Now if we have a quantitative trait, then we have few more options, and we can run a linear model, and even in the linear model we can test additive effect, genotypic effect, dominant effect, etc. So let's look how we can run a linear model when we have a continuous outcome. So first we read the Plink file. We specify which phenotype file we want Plink to read, and then which phenotype of interest we have. So if you compare here, my phenotype name has become pheno1 now, which is a continuous phenotype. And I'm using same covariates in my linear model as I used in logistic model. Similar to this minus minus logistic option, if you want to perform a linear model, you can use minus minus linear option. And here my output file name I am putting as linear underscore additive. So by default, if you just type minus minus linear, it will run additive model. So here our output looks almost like the logistic regression output, except that now we have different test statistic. Now we still have 1, 2, 3, 4, 5 different rows for each SNP, 4 for covariate and 1 for SNP. But now we have a beta, which is slope of a line, and then we have a t statistic and a p-value corresponding to the t statistic. So Plink output changes last few columns depending upon what kind of test you have performed and what kind of model you are running. Now let's say we want to run a genotypic model. So here what it does is it runs genotypic model by putting each genotype as a separate category. So now we have 3 separate categories for each SNP. So it will run ANOVA instead of just fitting one linear line. So with minus minus genotypic option in addition to linear, we can get genotypic effect. And I'm calling that output file to be linear underscore genotypic. Now here what we have is extra rows. If you look at this particular row, now in this case, because of low allele frequency, it just didn't create any output, but let's look at this particular row. So we have this additional line called geno underscore 2 degrees of freedom, or 2df. So this is a genotypic effect, and it's a 2 degree of freedom because we are basically performing ANOVA, and we have 3 different genotypic categories. So that's why it's a 2 degree of freedom test. And these are corresponding p-values. And there is no beta for 2 degree of freedom test. So that's why we have NAs here. So this is how you can perform genotypic test when you have a continuous outcome. So once we perform association analysis using appropriate models and we have output, there are few things you can add to the output, like you can annotate your association result, and Plink adds some information to the table like gene name, and if the marker is not on gene, if it's close to the gene, it will tell you how far it is from gene boundary, etc. So to do this annotation, we need to download this file called attrib equal to snip129.attrib.gz, and you can download this file from Plink website and keep it in .gz format in the same folder where you have all your data set. And the way you can annotate your result is, now with Plink we don't need raw data because we have already performed association analysis. So instead what you do is give option minus minus annotate and specify the result file that you got from your association analysis. So here I'm using linear additive ASOP linear file, which was my output from linear model analysis. And then I'm specifying this file, attrib equal to this, and here is the gene list file, which again you can download from Plink website. This file has gene ranges, so that's how it puts all the SNPs on appropriate genes. And then I'm calling this output file as linear additive annotate file. So basically what Plink does is it looks for SNP position, and based on gene range it will annotate each SNP if it has any information about the SNP. Okay, so it finished doing annotation. Let's look at the output file. The extension is .annotate. And if you see here, like I said before, it will put information in annotate column if it has any additional information, like if the SNP is on a gene or not. So you will see information wherever necessary. So like for these SNPs, they're on this particular gene, and if the gene is not, a SNP is not on a particular gene, then it tells you how far it is from a gene boundary. So this is how you can add extra information to your result table. Now there is another test you might want to run after you perform GWAS and SNP based analysis. What you can do is you can have a gene based or a set based association analysis. Now it's basically a set based analysis, but your set can be what you defined it to be. So if you define your set to be a gene, then it becomes a gene based analysis. If you want to include multiple genes in your set, then you can do that. All you have to do is define set the way you want it to be. Now for this particular example, I'm going to choose my sets to be genes. So I'll have a gene-based association analysis. Now to do that, I'll have to create sets. Now you can manually create sets as per your requirement, or if you happen to choose gene as your set, then there is one command in Plink that you can use to create this set file based on gene boundaries. So for that, what we need is this gene list file, which I showed you before and we used before, and with this option --mec set, it will create a set file for you, and then you can use that set file in your set based analysis. So in this case it will become a gene based analysis. So you read your exome CHR22 clean data, you make sets using gene list text, and with a write set option it will create output file with the set names, and I want the name of that file to be gene underscore set. Now if you look here, Link is saying it found only 153 ranges with at least one SNP in it, and 18,905 are empty ranges. Now this happened because we have a small part of genome as our data set. So within our part of data or genome, it could find only 153 genes that had valid information. The rest of the genes didn't have any SNPs in our data set because we don't have genome-wide data here. So if you look at the gene set, this is how it looks like. So typically if you create manually, you'll have to write a set name. In this case it's a gene name, and then in the next line you start typing SNP names, one in each row, and to end your set type END. So for all these genes or sets we don't have any markers. So let's scroll down, and for some of them we might find, like for example this. So for this gene, which happened to be on chromosome 22, we have these SNPs, and with the end we end the set, and that's how Blink knows that these all SNPs belong to this particular set or gene. So now we are making use of this set file to run gene-based analysis. So to run that, what we need is first the data set, then a phenotype name, and then if you want you can also use covariate, because this is exactly going to be like running linear or logistic model. So I'm selecting Pheno 1 here, which is a continuous outcome, but I'm not using any covariate in this, and I'm running a linear model. Now I'm using these extra options here. I'm asking Plink to perform a set-based analysis. So this option --set -test will do that set-based analysis. And then I'm telling Plink what my file name is for sets. And after that, there are 3 options you can use to perform this set-based analysis. Now remember, we have a certain number of SNPs in one set or one gene. Now, it's up to you if you want to use all the SNPs on a gene or just few of them based on three criteria. So first criteria is R square value. So if you don't want to use all the SNPs in a gene because they might be in LD, you can specify what LD threshold you want Plink to use while selecting those SNPs. So if you use minus minus set minus R square to be 0.25, then it will only use those SNPs which have LD less than 0.25. Anything above that, Plink will omit them. Now another option is based on p-value. Now the way this gene-based analysis is done is it runs association analysis first for each SNP, and it uses those p-values and get a combined p-value for the gene. So using this minus minus set minus p option, you can specify which SNPs you want to use in gene-based analysis based on their p-value, individual p-value. So with 0.5 option, what I'm telling Plink is use only those SNPs which had p-value less than 0.5 individually. And then there is another option, is minus minus set minus max, which tells Plink how many maximum number of markers you want to use in a particular gene or set. So in this case I am using 10. So anything above 10 it won't use. And this is a permutation based test. So you have to specify how many permutation you want Plink to perform. Now larger the number, more precise p-value you will get. But it also means that it has to run so many permutation. So it means that it will going to be that much computationally intensive. So for this example only I'm using 100, but based on how precise p-value you want, you have to use at least few thousands. And like I said, rest of the part is same as running linear model or logistic model. So I'm using linear and I'm calling output to be gene association. Now this will take a little bit longer than usual because we are doing permutation based test. And here it shows what permutation is going on right now. So you can get idea how long will it take. Okay, so gene-based analysis is over, and let's take a look at the output file. The extension for output file is mperm. Now again, it shows output for all the genes, whether they have SNPs or not. Now, since we have like 18,000 plus genes, there are 18,000 plus rows. But in our analysis, we will have p-value only for a few genes that are based on our data set. So let's find a gene that is appropriate for our data. Okay. So here's the output for this particular gene. and it shows number of SNPs based on our threshold. So based on the R-square value, uh, there were only 11 SNPs left in analysis that had less than 0.25 R-square. And then we had a p-value option. So after that there were, to begin with there were 11 markers. After R-square threshold there were 7 remaining. And based on p-value, there were only 5 markers remaining. So Plink used those 5 markers to perform gene-based analysis. And these are the list of those 5 markers. And this is a p-value computed using permutation-based test. So this is how you can perform a gene-based test in Plink. So overall you can perform either dichotomous outcome or continuous outcome models and association analysis using Plink. And you can use Plink for either unrelated individual data or family data, although the family data analysis we haven't covered in this video. But again, for each of the models we ran today, there are many more options within Plink that might be helpful for you to read. So if you go to Plink website, they have examples of each option, how to use and how to understand and read the output, which will be really helpful if you want to do GWAS on the real data. So we end this video here. Thank you.